Hello, this physics video is on the Carnot cycle, and I'm following Young and Freedman's University Physics. We are in chapter 20, which is on the second law of thermodynamics. So in this chapter, we've talked a little bit about the loss of heat that is inevitable in this universe. And we talked about engines and engine efficiency, and then we talked about refrigerators and refrigerator efficiency. Well, there's a guy by the name of Sadi Carnot who in the early 1800s asked this question: what is the maximum possible efficiency that you could have in a heat cycle where you have expansion and contraction and heat added and heat lost and so forth? What would be the maximum possible efficiency of that sort of a cycle? And he rightly concluded that the real heat loss and so forth occurs, the loss of efficiency happens when processes are irreversible. That is, when you can't put the genie back in the bottle. You can't put Humpty Dumpty back together again. And so he correctly induced or deduced that a heat cycle that avoided irreversible processes would be the maximal would have the maximal efficiency in that sort of a cycle. And this is thus therefore named after him, the Carnot cycle. And so it's a heat cycle, so there is heat coming in and heat going out. But he correctly suggested that if all of the heat transfer in this cycle was isothermal, so you don't have the heat coming in and out in a way that jerks the system, and you lose a bunch of heat. But the heat transfer is isothermal. That would therefore not, it would be reversible because it's isothermal, and we're not losing heat in that sense. And then that the temperature changes, so you have to have temperature changes, that the temperature changes would happen in an adiabatic way. So the temperature would not change with the change of heat. There would be no heat. Adiabatic means no heat added or lost during that process. So we would change the temperature without adding or losing heat. And when there was adding and losing heat, it would be done at the same temperature. And if you can do that, then you have the maximal possible efficiency for a heat cycle. So here are the steps that he suggested would do that, the Carnot cycle. And he started with the ideal gas, the idea of an ideal gas, although as we find out, the Carnot cycle works this way for any working substance. But we started with an ideal gas because we can make more assumptions about an ideal gas. For example, for an ideal gas, we know that the internal energy of an ideal gas depends only on the temperature. Things like that you can assume with an ideal gas that you can't assume with other things. So step one, he said, let's expand. Let's say you have a piston. Let's absorb the heat at the same temperature. There will be a volume increase, but perhaps it can happen slow enough that there's not a change in temperature as it's absorbing the heat. So as you're absorbing the heat at the hot side, you're staying at the same temperature. Okay, so step one, expand whatever it is, the ideal gas, isothermally at the same temperature, TH, while absorbing an amount of heat, QH. Then, once you've absorbed the heat you're going to absorb, expand it adiabatically to a different temperature, that is, without adding heat, from TH, the hot temperature, to TC, the cold temperature. Okay, so that's one half of the cycle. Next, when we're going back toward the lower volume, first of all, compress it isothermally at the same temperature while throwing off that extra heat to the sink. So the heat that you've gained, you're throwing it off now to a sink, but you're doing it at the same temperature, right? So it's a reversible process. And then finally go the rest of the way to the lower temperature. Once you've gotten the heat out, then decrease the temperature adiabatically, which means without involving heat. And so additional heat. So this, Carnot correctly suggested, would be the most efficient heat cycle that is attainable in this universe. Okay, so here's a diagram of it, which I've drawn. These are isotherms, these lines right here. So everything is at the same temperature. This is a PV diagram, so we have pressure and volume, right? So the first step of the process, we are adding heat, but it's staying at the same temperature. So we're expanding isothermically, and QH is the amount of heat that we're adding. Then once we've finished adding the heat, we will go from the higher temperature at this isotherm to the lower temperature at this isotherm, but we'll do it adiabatically. So we're not going to, there's not going to be any addition of, or there's not going to be any loss of heat. I'm sorry, or expanding the volume. There's not going to be any addition of heat as we go from here to here. Okay, that's part one of the cycle. Now, as we go back, we're going to throw off the heat that we had gained into QC, and we're going to throw that off into the sink, but we're going to do it at the same temperature, so it remains a reversible process. And then once we've thrown off the heat that we had added, the QH and QC are going to, you know, I think be roughly the same. And so now we're going to go to the higher pressure, the volume decreasing, as we're going to do it adiabatically. So we're going to do it without to the higher temperature without adding any heat to the system. Okay, so here you have the Carnot cycle, nicely pictured. And so that is the Carnot cycle. Now, so what is the efficiency? What is the thermal efficiency of a Carnot engine? Well, as we just said, for an ideal gas, internal energy depends only on the temperature. And so in an isothermal process, the heat added is going to be the amount of work done. So the work to get from A to B on the first part of the cycle is going to equal this. We know this from a previous section, back in section 19.2, in one of the examples, this was proven, you know, that basically in this situation, in an isothermal process, the amount of heat that is in the hot part is the amount of work done, and it's nRT at that higher temperature, a natural log of the ending volume divided by the starting volume, okay? And we can say the same thing for the heat at the cold side, that the work done getting from C to D is going to be negative because we've flipped the direction, right? So B is the final point and A is the starting point. But here, C is the starting point and D is the ending point. So we flipped the order, and that's in part where the negative comes from. Okay, so we have these two. So if we divide QC by QH, what we're going to find is that the natural logs, there's more in the book. I've skipped a few steps, but basically we're going to find that this natural log and this natural log are the same, so they cancel out. And then NR and NR cancel out. And so we are left with just the Q at the cold side and the Q at the hot side is going to equal the temperature, the negative of the temperature at the cold side divided by the temperature at the hot side. Now, we know from an earlier section that efficiency for an engine is 1 plus this ratio. So we can substitute this in, and we're going to get 1 minus TC over TH, right? And if we make TH over TH, if we make the 1 TH over TH, we get this, all right? We're getting somewhere here. And so this is the efficiency of a Carnot engine right here, the efficiency of a Carnot engine. All right, Carnot Refrigerator. This process can run in reverse, so it doesn't have to just be, you know, the heating bit. It can be a cooling bit. And so this entire cycle can be reversed. You might remember earlier in the chapter, we talked about the coefficient of performance in talking about refrigerators in general, capital K, and that the coefficient of performance is basically the absolute value of the heat thrown off divided by the amount of work done. And so we can basically substitute in from previous equations, and we've got W equals QH minus QC. All right. So this is all from previously on heat. So if I divide both the top and the bottom by QH, I get QC over QH and QC over QH. Well, I just had an equation for QC over QH, right? And basically it involved the temperature. And so this on the top equals TC over TH, and this on the bottom equals TC over TH. And so all I need to do is cancel out some things using good old algebra, and I end up with this equation for the coefficient of performance for a Carnot refrigerator. So some equations there that will help you in your exercises. This has been the Carnot cycle. I will have, I'm dividing up 26 into 2 videos. So the first video on the Carnot engine and refrigerator ends here, and we'll be back in just a second with Carnot, the second law of thermodynamics, and the Kelvin scale.